Hello everyone, again, welcome back. And in this video, I am gonna do the data processing. In the last video, we have extracted the frames from the video data, and in this video, we are going to make the NumPy arrays by, appending each of the images of the frames into valent and non-valent. Let's see what we can do here. So let's get started with the video here. Okay, so this is the these are the the parameters or the fixed variables that I have defined in the last video. Just gonna run it, and hopefully this kernel is still active. Yes, it is. Anyways, okay, so let me start this video by creating a function where I will define the dataset, or create the dataset. So defining as create data sets, not gonna take any parameters, it's just gonna be a normal function. Gonna have a dataset array. Now we have to limit the image to 10, so we need a counter for that, and as well as we need a counter for the entirety of the the entirety of the number of frames there are in total in the our data frame folder. So also we need an images array to store the 10 images that we are planning to populate with with 10 images of label, 10 images and a label. Okay, so we know that the first 2049 images are of non-valent dataset. So the non-valent dataset would be 0,1 in our case, and the valence would be 1,0. That's how we're labeling, as we saw that in the architecture it has two neurons, for one for valence and another for non-valence. So that is what we are going to do. Gonna use this and then to iterate through all of the files in for frames in was just list directory data frames. So this is iterating through all of the also I'm gonna give tqdm or see the iterations. All right, so now for the frames, what we're going to do is to convert it to read it and then convert it into a NumPy array. So first we need to join the files. So path equals os.path.join. The parameters are the first path that is of the bytes. So sorry, it's data frames, and then the second parameter would be the frames that we are getting. Now to read the image, we need to do I don't need to resize it because it's already resized. Let me just again check. Each of this is of size. Come on, it's not exactly 3. It did not resize. Let me see it. Yeah, we did not. We need to convert it. So going in the name of image, img is equals to cv2.resize. cv2.read to read the image, and the read which image? The image in the path, and resize it by image sizes by image size. Image size, image size. Yes. Yeah. So that's gonna hold the image. Now we are going to append the image to the images array. Append as an NumPy array of image. Yeah. We did import NumPy, or I did specify NumPy as np. All right. So we are appending, now increasing the limit because we need to, like, count the limit if it's 10 or not. So, and also increasing the count by 1. So it will check if limit here, limit is equals to the number of frames. Do I have a number of frames? No, we don't. So let's just specify frames equals 10. We need 10 images per, the sample. Now, okay, so here the limit is the number of frames, which we specified it to be 10, and if the limit reaches 10, we will set the limit to be equal to 0 again, and then append the 10 images in the images array to the dataset. I hope it makes sense. So I'm just gonna do dataset.append, and I'm gonna append these as a NumPy array. Yes, I need an array of NumPy array of the images, and the NumPy array of images, and a NumPy array array of now I'm putting now the labels. Here would be the first label, NumPy array, and this. Okay, so I'm going to use this counter to see if we know that the first from 0 to 250 wait, let me just see, 0 to 249 images are 20,499 images are of what do you call it? It's a non-violent set. Did I close it? The properties. Wait. Let me just see. It's 20,000. 400 and this is a non-violent? Doesn't look like one. 20,400 and okay. Till that. I guess these are of violent sets, so it's 20,416. 20,416 frames, and afterwards all of them are violent. So I'm gonna iterate through the 0th till the number of 20. Like if C is less than 20,417, then I will append it like this. Else LF is greater than or equals 20,417, then I'm gonna append. I'm just gonna copy this line. Alright. I'm just gonna change it to 1 and a 0. Hopefully it will, everything will be in a NumPy array, and after appending I don't have to shuffle the data because I am going to, I do have to save the data in NumPy, like NumPy file, and I have to return the data set. But I don't think I have to change the shuffling, or I can shuffle. Let's just shuffle. Let's shuffle. No, there is no harm in shuffling. So after the for loop has been completed, just gonna use the shuffle and put in the data set. Yeah, and then np dot save. I'm gonna save the dataset as dataset.numpy. I'm gonna save what? The dataset. And what? Then return the dataset. Now this is the function. Now I have to run the function. Data equals to create dataset function. Now it's gonna take a while. I hope it will not crash my system. Yes, now let's just start it and counts. Okay, and local variable C is defined before the assignment. Okay, yes, of course. This around count, but I use C, and anywhere else? No. Redefining the function, executing the cell, local count, C count. Oh, nice. C count. Okay, anywhere else? Count. Redefining the function, running the cells, num variables is not defined because we did not do this, creating that. Now it's going on. Okay. Alright, so deprecated. Interesting, it is going on. I just used TQDM in here, so it's number of frames. Yeah, it's going alright. Let me see how much RAM it's taking. Not much. Okay. Yeah. Okay, so alright, let me just see if everything is alright in here. So the next thing we have to do is to check if it's alright. Like, I have shuffled the data, so the last part of the data would be the last part of each samples here would contain the random or other would contain these two as random orders. Now I can trained test split. Gonna use a trained test split later. What I have to do now is to I can start making the model now. Let me just see. Do I need to do anything else? What the hell? Yeah, okay. Alright, that's good. Now I have to start making the model. Okay, so this is the portion where I'll be making the model, so I'm just gonna comment it out like model. Creation. Alright, yes. Okay, now I need to import a few dependencies for which I'm gonna need to find the model. Gonna copy the dependencies here. So from Tensorflow, Keras, layers, I'm going to import the LSTM, the bidirectional, the conv, 2D, dense, flatten, max pooling, time distributed. These are the things that I think I would need. So in here, okay, so this is the exact model that we have done the frame, like the distribution part. Now we understand that we need to put it into the CNN layers and then flatten it down and flatten here and then feed it to the bidirectional LSTM into the denseness and out to the output. So this is exactly the entire model. So making the model, the first is the input convolution plus ReLU, convolution plus ReLU, then the max pooling. So there's like 3 convolution blocks followed by 3 ReLU. So just gonna first define, let us define the convolution. So gonna start with model equals to sequential. This is gonna help us keep adding the layers one by one. So that's gonna say just model.add. This would be the input layer, the input convolution that we have seen. If I can just show you again, this would be the input, like the purple, this one, the input convolution plus ReLU. That is what I'm trying to do here. So that would be of 64. Let me see. There, it was 64. 33, 64 kernels, STM 01, max pooling in 2x2, each max pooling. So every convolution layer is 64. It has 64 different convolution filters. It's 3x3 convolutional filter size, and then the max pooling filter size would be 2x2. Everything is ReLU, has a ReLU activation function, so yeah, that's gonna do that. So I'm gonna use 64 comma specifying the filter size, which should be 3,3, specifying the activation. Activation, I hope it's right. I'm gonna activate and give it ReLU, not ReLU. ReLU, and gonna specify the input shape. Now, to see the shape, that's something not exactly like we need the shape of the convolution to be of 10 comma image size comma 3 because of the 3 channels. So the 10 is like the 10 sample, the video samples, the 10. In each sample there are 10 frames. Each frame has a width of 100, height of 100, and RGB channels. That's all. So I'm gonna make sure that the padding remains the same here, so that, like, you know, when this layer feeds its output to the actual convolution, it is like, you know, it is keeping the same, you know, the height and width. So I'm just keeping the padding to be same. All right, so next, to add the conv layer. So this is exactly not the input, so just gonna add it on top of the conv layer that we have like made, containing 64, having 3,3, and an activation function of ReLU, and then no input size, I think. Yes, then gonna specify the max pooling to be 3D. So here would be the problem. We can use max pooling 2D, or we can use the max pooling 3D. But I think I am going to use the max pooling 3D because the, you know, the output that we are getting from the second convolution, the main convolution layer, this one is exactly it's not exactly image of, you know, image of height, width, and RGB. It's exactly height, width, RGB along with 10 images. So the max pooling will not be only on the, you know, the first image, but also in the consecutive images. Okay, so I'm going to use max pooling 3D here. Gonna specify the max pooling layer as it's a 3D filter, so I'm gonna specify as 1, 2, 2. 1 being like it's gonna, you know, do the max pooling in each of the 10 frames, and 2x2 is the actual filter of the max pooling. Yeah, I'm gonna do it 3 times here because there are 3 layers. Activation of ReLU, max pooling. Yeah, yeah, that's the thing. Yes. Now we have to, you know, the flatten. Looking at here, the shape would be. We're done with this part of the model. Now we're gonna do the flattening part. So to flatten the model, if we use the model to flatten, this will not exactly work because it will flatten all of the pixels in a one single column, like all of them. It will not, you know, specify the 10 frames, the 10 separate frames that we will need to, you know, put into the LSTM layers. The LSTM is requiring us, I'm going to tell you in a bit, but before I tell you this, we can use flatten if we were to, you know, send this output of this max pooling directly to a dense layer. If we were to do a dense layer after this max pooling, we could have just flattened it and just, you know, sent it. If we did that, we would not have been, you know, needing this 10 also, because we just specify a sequence of images, like consecutive sequence of images here, because we, like, you know, we need the LSTM layer. The LSTM needs a sequence. Without the sequence, the LSTM is just basically a dense layer. That's it.
This is a bidirectional LSTM. So what we need is to define two different. We're not going to use the flatten. So we're just going to cut the flatten and add a reshape. So add a reshape to shape it into something more manageable. So I don't exactly know that what will it took. I do know that it's gonna take the 10 here. It's gonna keep the 10. It's gonna keep the 10, and next there will be a value of whatever that remains exactly. So it's gonna take the 10, and I need to see if how many cells come out of the last max pooling layer. What we can do to find out the last layer is, like, comment this out, and I guess I can see the summary. I think, hopefully without any errors. Okay, yeah. So yeah, as you can see, the last max pooling layer is giving us 10, 10, 10, 64. So that's what we are going to use. We're going to keep the 10 here, but we are going to, like, multiply these out and use this. So this is what we're going to do. Cut the summary here, and we're going to use 6400. That's the product of 10 times 10 times 64. So that's what we're going to do here. We're going to reshape. Like, after reshaping is done, we can, like, define two different LSTM blocks, which will one go forward and one go backwards. If we can, like, check how many cells are there in a LSTM block they have used. This is the CNN bidirectional LSTM, long short term. 0 and 1, forget layers, blah blah blah, sigmoid. They did not exactly mention here. I'm gonna use some arbitrary value here, like, just to, like, get on with the tutorial. So gonna define the LSTM forward layer being the LSTM layer and having the units of 30. Also the LSTM backward layer, and defining it to have the units of, again, 32. Now to make the adding the bidirectional into our existing model. So I'm just gonna do a model.add, and then bidirectional, gonna specify the LSTM forward and specify the backward layer to be the LSTM backward. Yes, the forward and the backward. This is specifying the entirety of the LSTM layers here. Okay, now we are gonna define the dense layers. Let me just, comment it out for best practices. By LSTM layer. This would be the layers. Sorry. Okay. Now to the dense layers. Layers, I don't know. So they used 2 layers. So we are also gonna use 2 layers. Okay, something's wrong with my music. Okay. All right. So the dense layers now. So the dense layers I am specifying 2 dense layers for, like, the training. So I'm just gonna add 2 dense layers, dense and having the units of 64. Is it 64? Let me just check. Dense layer comes to deep learning, dense help layer, okay, random blah blah blah, pass 3 focus of activation function. Okay, so yeah, it does say 64 and 32. Nothing else. Okay, yeah. I'm just gonna use the 64 and 32. 64 of an activation of ReLU. Same. 32. Activation of ReLU. And then the last layer would be the dense, having 2 neurons, and that would be my output layer, and that would have the activation to be sigmoid. Well, apparently the sigmoid was used as an activation here, but the better one would have been the softmax. Anyways, now we are going to see the entire summary of the model that we created, and we will not exactly compile because we cannot compile because of the errors. Nice. Forward and backward have different go backwards value. Alright, so what did we do wrong? Okay, yes. Need to specify a go backward here because we are specifying this to be a backward layer. So backwards equals true. Yeah. How it works? Yep, we are done creating the model. In the next video, let me just check the first con, the second con, max pooling, cons again, max pooling again, conv again, max pooling. The 3 cons done, then the reshape, the bidirectional, then the dense, the dense. Okay, one thing I was about to tell about the input LSTM layers take. So the input LSTM layers tend to take are 3. The first would be the number of elements in a batch, like how many elements you are pushing from below. The next is the number of the sequence an LSTM has. I cannot visually explain it with my hands. I'm gonna make a separate video explaining LSTM cells and their inputs and outputs. And this is the amount of each of the LSTM cells would have input of 6400. So yeah, that's about it for this video. In the next video, we are going to compile this model, reshape the training. So yeah, we did have the data in our data set. I guess I'm gonna have to see it in the next video. Gonna have to reshuffle it, split it into 90 and 10% by the train test split, and then hopefully we can train the model and see the validation accuracies. Yeah, that's about it. So I'm gonna see you in the next video. Thank you very much.